Welcome to this presentation on an introduction to partial fractions. Within this presentation we'll look at problems involving linear factors, repeated linear factors and quadratic factors. Just an overview to the presentation on partial fractions. We're going to consider why we need to use partial fractions, the three types of partial fraction available to us, the solution formats for these types of partial fraction, the two conditions we must check that are satisfied before we commence a problem, the solution methods we can use. There are three: substitution, comparing coefficient and the Coverup Rule. Example 1 will involve linear factors, followed by some exercises for you. Example 2 will consider a repeated linear factor problem, followed by some exercises. And example 3 will consider a quadratic factor problem, followed by some exercises. And I'll leave you with some tutorial questions. So why do we use partial fractions? Well, often it's to simplify other problems, maybe in terms of differentiation or integration. The functions we're given to solve or we derive are difficult to solve as stated, so by going into partial fractions we make those functions simpler. For example, on the left hand side, this function here would be quite difficult to integrate, but if we factorise the denominator and remove two partial fractions, these are the partial fractions here, these will actually be much easier to integrate. So it helps us in our solution process. There are three types of partial fraction to be aware of. The first type is the linear factor. And these are linear factors: the x over the x minus 2 plus the 3 over the x plus 1. The x minus 2 is a linear factor because it's a linear function of x, and the x plus 1 again is a linear function of x. One of the processes we need to be aware of in the coming problems is making common denominators of our partial fractions. Just talk you through this for a moment. So the common denominator for x minus 2 and x plus 1 would be x minus 2 times by x plus 1. And again, that's just basic fraction. If you go back to basic arithmetic of fractions, when you're trying to find common denominators, that's the process you use. What we've got to be careful of is that we factor the numerators correctly. So the 1 is factored by the x plus 1, and the 3 is factored by the x minus 2. In this way I do not affect my overall fractions. If you look at the fractions, I've still got 1 over x minus 2 because the x plus 1 on the top cancels with the x plus 1 on the bottom, and I have still got 3 over x plus 1 because the x minus 2 on the top cancels with the x minus 2 on the bottom. We'll look at that in more detail later on, but we need to be aware of that process. And in a lot of the cases we'll start from this compound fraction and we'll be moving into the partial fractions. Type 2 is a repeated linear factor, and such expressions include something like 3 over x plus 1 plus 4 over x plus 1 all squared. The squared is outside the bracket. This is classified as a repeated linear factor, and again in some cases we will need to have this common denominator, which would be x plus 1 all squared in this case, and again we need to factor up the numerators appropriately to make sure we don't affect the original fraction. And the third type of partial fraction, the most difficult to solve usually, is the quadratic factors. This is where we have an expression like x squared plus 5x plus 2 on the bottom line, and that bracket will not factorise. So we have a function of x over a function of x, but it does not factorise. In this case I've also shown a linear factor associated with this problem as well. So the first term there, the first partial fraction, is a quadratic factor where we have an x squared on the bottom line in a bracket, so the square is inside the bracket, and the second term is a repeated linear factor. Again, we will have to find common denominators of such things, and the common denominator would be the x squared plus 5x plus 2 times by the x plus 4 on the bottom. And again, you would need to factor the top appropriately to make sure that we do not affect the overall fractions. For the various questions we're going to look at, we need to be aware of the type of partial fraction we have. So we need to look at the three types of partial fraction form we will come across. If I take linear factors are the form of a function of x over, and these are linear terms here, an x plus a in a bracket, an x minus b, and an x plus c. It's a generic expression for us there, but it shows the format here. So all the terms are linear factors on the bottom. The solution format in partial fractions forms would be written as a constant, over x plus a, in this case plus b, over a constant x minus b, plus c over the constant x plus c. If we only had the x plus a and the x minus b bracket on the bottom line, we would only have the a and the b terms here. Looking at repeated linear factors, this would be something like a function of x over x plus a. I've shown it all cubed here, but it could be to the power 2 or the power 4 even. If it's to the power of 3, our solution of partial fractions will be in the form of a over x plus a plus b over x plus a all squared plus c over x plus a all cubed. If it's only a squared term outside the bracket, I would only have the a and the b terms. If it was a fourth power outside the bracket, I would have a d over x plus a to the power of 4. And the final solution type is the quadratic factors, where we have a function of x, in this case over a bracketed term that will not factorise, the ax squared plus bx plus c, it doesn't factorise, so the squared term is inside the bracket this time, and I've shown a linear factor associated with that just for a variation here. The solution to the quadratic would be ax plus b over the ax squared plus bx plus c, so that's purely for the quadratic term, and then in this case I would have a linear factor also added to the solution. There are important conditions we need to check that are satisfied before we start resolving into partial fractions. The first one is that the numerator is at least 1 degree lower than the denominator. That means in this case, this example, 4x minus 5 is in the numerator, the x is to the power 1, we don't write the 1's but it's there, and the denominator is x squared, so it's a higher power on the denominator, so the condition is satisfied. In this example here, the condition is not satisfied because in the numerator we have an x cubed and the denominator we have an x squared. So we would have to use something like polynomial division first of all to reduce the order of the numerator before we could use our partial fractions method. But you will not be asked to use polynomial division within this presentation. The second check we perform is just to check if the denominator will factorise. If it does, we're able to use the type 1 and type 2 solutions of partial fractions. So for example, the x squared minus x minus 2 does factorise to x minus 2 x plus 1 in brackets, and the 2x squared minus x minus 1 also factorises to brackets. So we could use type 1, type 2 solution. If they do not factorise, we are left with quadratic factors. There are three methods for finding the constants, the a, b's and c's in our partial fractions, and we'll consider all of these methods in the solutions we're going to look at. The first one is substitution. This is where we will rearrange an equation and we will substitute values of x into it to solve for the a, b's and c's. We can use this for linear factors and most repeated linear factor problems. Method 2 is called equating coefficients. This is the most comprehensive method. This works for all problems, but it can sometimes be a sledgehammer to crack a nut for simple problems. But it certainly solves any partial fraction problems you would come across. And the third method is called the Coverup Rule, or the finger rule here. It's very similar to substitution, but it only works to solve linear factors or the highest power of a repeated linear factor. So that's its limitations. Example 1, we're asked to resolve the function 3x minus 2 divided by x squared minus 3x plus 2 into partial fractions. We undertake our checks. The numerator is lower order than denominator. In this case our numerator is x to the power 1 and the denominator is x to the power 2, so we've satisfied that check. And does the denominator factorise? Well, the x squared minus 3x plus 2 does factorise into brackets of x minus 1 and x minus 2. I suggest you just check that for yourself there. So we can take our fraction, compound fraction, and write it as 3x minus 2 over the factorised form of x minus 1 and x minus 2 in brackets. From previous table, we know the output format in partial fractions for linear factors, which these are, is a over x minus 1 plus b over x minus 2. These are linear factors because they have no squared inside or outside of the brackets. The next line, I'm taking my common factor, common denominator on both sides of the equation here. So again, be careful how you factor up the numerators. I've got a times by x minus 2 plus b times by x minus 1. Again, think this through very carefully. I mustn't change the a over x minus 1 fraction or the b over the x minus 2, but when I write over common denominator I need to factorise the numerator. So a times x minus 2 will then cancel, the x minus 2 on the top will cancel with the x minus 2 on the bottom to leave me with a over x minus 1. And if you take the second term, the b times the x minus 1 on the top line, that cancels with the x minus 1 on the bottom line to leave me with b over x minus 2. You need to think that step carefully through for yourself there as to how we arrive at these common denominators. Okay, example 1 continued here. I've just repeated equation 1 for convenience. What we're going to do now is equate the numerators on both sides of the equation to form equation 2. So looking at equation 1, I have 3x minus 2 on the left hand side for the numerator, so 3x minus 2 here, and I have the a in brackets x minus 2 plus the b in brackets x minus 1 on the right hand side. So that's how I get equation 2. But please note, you can only equate the numerators when the denominators on both sides of the equation are the same. So in equation 1, the denominators are the same on both sides, so I can equate the numerators. I'm now going to solve for my constants a and b. I'm going to use method 1, which is substitution. With this method, we simply say to ourselves, looking at the brackets on the right hand side of equation 2, what value do I make x to make the bracket associated with the a go to 0? Well, I need to make x equals to 2. And all we do is put the value of 2 into equation 2 wherever I see an x. So on the left hand side I've got 3x minus 2, so that will be 3 times 2, take away 2, that will give me 4. Do the arithmetic on that. On the right hand side I have a open bracket x minus 2, so I'll put the x equals to 2 in there, and that will disappear, a times 0. And then I've got b open bracket x minus 1, so that will be b open bracket 2 minus 1, that will give me 1b, or simply b. So b is equal to 4. I found my first constant. Going to the next bracket, x minus 1, I need to make the value of x 1 there to make that bracket go to 0. So again I place the value of x equals to 1 wherever I see an x in equation 2. Left hand side, 3x take away 2, that would be 3 times 1 take away 2, that gives me 1. On the right hand side I have a open bracket x minus 2, so that will be in this case a open bracket 1 take away 2, and the b bracket will disappear as it goes to 0. Again, doing the numbers on this, we find that a is equal to minus 1. So we've solved for our two constants. I'm just going to take you through method 2 here to show how the comparing coefficients works for the example 1. Again, I've repeated equation 2 for convenience. What we do with comparing coefficients is we generate equations based on, in this case, the x coefficient and the constants. So if you compare the coefficients on the left-hand side to the right-hand side for the x terms, and coefficients in mathematics means the numbers, the coefficient associated with the x on the left-hand side is 3. I've got 3x, so the coefficient is 3. On the right hand side, if you consider expanding the brackets here, you would have a times x, so a coefficient would be a on the right hand side, and looking at the second bracket, if you expand it, you would have b times x, so a coefficient is b. That gives me an equation. I cannot actually solve directly here because I've got two unknowns in the one equation, so I need to generate another equation. and we can compare constants on the left hand side to the right hand side. So looking at the constants, on the left hand side I have minus 2, okay, there's no x associated with it, so that's a constant. And on the right hand side, if you consider expanding the brackets, I would have minus 2a, okay, the a times the minus 2 expands in the brackets, and I would have b times minus 1 or minus b when I expand the second bracket. Again, take a note, a few minutes to sort of note what I'm doing there with the coefficients. In this case I get equation B. I've now got two equations with two unknowns in it. I can solve them simultaneously. In this case it's quite convenient. If I add the equations A and B, I will eliminate the constant B from the equation. So adding them, I get 3 minus 2 on the left hand side gives me 1. Adding on the right hand side A, take away 2a gives me minus a. The b minus the b goes to 0, and again I can show a is equal to minus 1, and then as usual with simultaneous equations, substitute the value of a back into, I've chosen equation a here to find b, so we can show that b is equal to 4. Same value for the constants as for method 1. Okay, example 1 continued here. I've just repeated this top line here for convenience. We're going to use method 3, the Coverup Rule, to solve for constants a and b. Don't forget that the Coverup Rule only works for linear factors or the highest power of a repeated linear factor. We can use it in this case because the a and the b relate to linear factors. To use this method, what we do is say to ourselves, taking the first fraction on the right hand side for a, what value do I make x to make that bracket go to 0? Well, if I make x equals to 1, that bracket will go to 0. 1 take away 1 will give us a 0. And then what we do is on the left hand side is we cover up the x minus 1 term and put the value of x equals to 1 wherever we see an x on the left hand side. So to find constant a using the Coverup Rule, in the top line we'll get 3x take away 2, so that'll be 3 times 1 take away 2, all divided by, on the bottom line, we would have x minus 2, so that's 1 take away 2. Doing the arithmetic, we get a is equal to minus 1. To find the b constant, we move to the right hand side here, and we say what do we make the value of x now to make the bracket go to 0. For the second bracket we make that x equals to 2, and then we cover up on the left hand side the x minus 2 bracket and then put the values into the remaining part of the equation on the left hand side to find the value of b. So in this case the top line will be 3 times the x, which is 2 take away 2, all divided by, on the bottom line we will have x take away 1, that will be 2 take away 1 on the bottom line. In doing the arithmetic, we find that b is equal to 4. All I've done finally is stated the original function and now the partial fraction, so it's a upon x minus 1, that's minus 1 upon x minus 1 plus the b upon x minus 2, so that's 4 upon x minus 2. All I've done finally is just slightly rearrange the equations, putting the positive term for the negative term. Okay, some tutorial exercises here purely on linear factors. Exercise 1, what you've got here is 11 minus 3x divided by the x squared plus 2x minus 3. Now that will factorise, okay, I'll let you do the factorisation on it, but you'll end up with two partial fractions, an a over a bracket and a b over another bracket, and the values of a and b you can see will be given here. And in exercise 2L here, you've got another linear factor problem. It's actually already factorized on the bottom. You have 3 linear factors here, and you can expand that as a over x plus 1 plus b over x minus 2 plus c over x plus 3. And again, you can see the constants here given to us in the answer. Again, I'll let you play with those and see how you get on with them. Example 2 here, we're asked to solve the 3x plus 7 over x minus 1 all squared here. Now that is in the format of a repeated linear factor because I've got squared outside of my denominator on the bottom line. Doing my 2 checks, the numerator is lower order than the denominator because it's 3x to the 1 on the top and an x squared if you expand the bracket on the bottom, and I'm already factorised on the bottom because it's already in the bracketed term, so my checks are satisfied here. So to resolve into partial fractions, I will get 3x plus 7 over the x minus 1 all squared on the left hand side, and from our previous table the partial fractions format will be a over x minus 1 plus the b over x minus 1 all squared, because it's a repeated linear factor in this case. Equation 1, I'm just making common denominators on both sides of the equation. I'm getting the x minus 1 squared on the left hand side and the x minus 1 squared on the right hand side. To do that, I must add the x minus 1 bracket against the a term so that it cancels with the x minus 1 all squared at the bottom to leave me with a over x minus 1. I mustn't affect the original partial fractions. The b is over the x minus 1 all squared, so it's just b on the top line. Once you have the denominators the same on both sides of the equation, you can equate the numerators. So equation 2 is the numerators being equated. Continue with example 2. I've just repeated equation 2 for convenience. I'm going to use method 1 here to solve for my constants a and b, and again same process as before. Using substitution, you have to consider what value of x you need in the bracket to make the bracket go to 0. So for the a term, a times the x minus 1 here, I will make the x value equals to 1, and I will solve for the b. So again, letting x equals to 1, all you do is put the value of 1 where you see an x. So in the left hand side of equation 2, I get 3x plus 7, so that's 3 times 1 plus 7, that gives me 10 on the left hand side. On the right hand side, put in my value of 1 for x, I get a times 1 take away 1, so the a disappears, and I get b, so b is equal to 10 in this case. Looking at the solution to find a, if I put the value of x equals to 0 into the equation, I will actually find the value of a, because I now know the value of b. So putting 0 into the left hand side of the 3x plus 7, I will get 3 times 0 plus 7, that will give me 7, and putting 0 into the right hand side of the equation, I get a times 0 take away 1, so that's minus a plus my 10. Again, doing the numbers on that, I get a equals 3. So we could use x equal to 0 there because we knew the value of b. Okay, continuing with example 2, I'm repeating equation 2 for convenience here. We're going to use method 2, which is the comparing coefficients. So in this case, I can generate two equations for the coefficients of the x terms and then the constants. So comparing coefficients of the x terms, on the left hand side the coefficient of the x is 3, I've got 3x, so the coefficient is 3, and on the right hand side the coefficient of the x terms, a times x, is a, so straight away a is equal to 3. Comparing the constants on both sides of the equation, I get on the left hand side 7 as a constant, and on the right hand side I get minus a, because minus 1 times the a, and I get plus b as a constant. So knowing the value of a, I can put the value of a in, so I get minus 3 plus b on the right hand side, and again doing the numbers on that arithmetic, I will get b is equal to 10. Okay, continuing example 2 here, I'm going to use method 3, which is the Coverup rule here. I've just repeated the above line for convenience. Now, with the Coverup rule, it can only be used to solve for the highest power of repeated linear factor. So in this case, the only term I can find is the b term. So in this case, using the Coverup rule, the value of x I need to make that bracket go to 0 would be x equals to 1, and then what I do is cover up the x minus 1 squared on the left hand side and simply put the value of 1 where I see an x. So I would get b is equal to 3 times 1 plus 7 is 10. I cannot use the Coverup rule to find constant a, I must use one of the other methods to do that. So the solution here is 3x plus 7 over the x plus 1 all squared, our original function given, and we've shown that is now 3 over x minus 1 plus 10 over x minus 1 squared in terms of partial fractions. I will leave you again with some repeated linear factor exercises, just sort of talking you through briefly. In exercise 1R, you've got 2x plus 3 divided by the x minus 2 all squared, so your partial fractions would be a over x minus 2 plus b over x minus 2 all squared, and then you have two constants a and b to find. In exercise 2R, you've actually got a linear factor first of all, and a repeated linear factor, so be careful of that. So your output partial fraction would be a over x plus 3 for the linear factor, and then b over x minus 1 plus c over x minus 1 squared, and the a, b's and c's are given in the solutions there. And the final partial fraction here to look at for the exercise 3R, you've actually got in the denominator a cube term here, so your solution of partial fractions would be a over x plus 3 plus b over x plus 3 squared plus c over x plus 3 cubed, and the a and b and c are shown here. Example 3 here, we're asked to resolve the expression 2x plus 3 over the x minus 2 x squared plus 3 into partial fractions. We do our checks again. Is the numerator lower order than denominator? Yes, it is. We've got an x to the 1 on the top, and if you expand the bracket at the bottom, you actually get an x cubed, so that's satisfied. And we're already in bracketed terms in the bottom line, so we've already done as much factorization as we can. The problem we need to be aware of here, though, in denominator here we have an x minus 2 function, which is a linear factor, but because we have an x squared inside the bracket here, that is a quadratic factor. So when we expand in terms of our partial fractions, we will get a over the x minus 2 for the linear factor, and then we'll add to that the bx plus c over the quadratic factor of x squared plus 3. If you go back to the previous table, it shows you this format of bx plus c over the quadratic factor. To get equation 1, again I'm trying to find common denominators on both sides of the equation, so again be careful how you do this. I will need to multiply the a in the numerator by the x squared plus 3, so it will cancel with the bottom term to give me a over x minus 2. And I will have to multiply the bx plus c by x minus 2, so that will cancel with the denominator x minus 2 to leave with the bx plus c over the x squared plus 3. Again, I encourage you to think through equation 1 and the way we found the common denominators. Example 3 here, equation 2, all I've done here is equate the numerators from the previous slide to get the equation 2. And equation 3, I've just expanded part of equation 2 to make the terms easier to understand. So on the right hand side I've left the a times the x squared plus 3 because that's clear to understand the x squared and the constant term there. But I have expanded the bx plus c times the x minus 2 brackets of equation 2 to give me the bx squared minus a 2bx plus the cx minus a 2c. Just an expansion of brackets there. It just makes the terms easier to see when you're comparing coefficients. I'm going to determine my constants here. I'm going to use the substitution rule. I can use it to find the value of constant a in this case. If I let the bracket x minus 2 in equation 2, if I make that go to 0 by letting x equals to 2, I will be able to solve for constant a in this case. I can only use it for constant a. So taking the left hand side of equation 2, I will get 2x plus 3, that will be 2 times 2 plus 3, that will give me 7 on the left hand side, and putting the value of x equals to 2 in the right hand side, I will get a times 2 squared, x squared is 2 squared plus my 3, and then I will get b times the 2 plus c, and then the 2 take away 2, that whole bracket term will disappear, so the b and c will go to 0, and I'll be left to solve for the constant a. So a in this case is equal to 1. So I can use the substitution rule to find the value of a, but not to find the value of b and c. Okay, example 3 continued. I'm going to use the Coverup rule here to find constant a. Don't forget, now the Coverup rule can only find linear factor constants or the highest power of repeated linear factor, so I can only use it to find constant a in this problem. To find constant a, I need to say what value of x do I need to make here for the bracket to go to 0. Well, x needs to be equal to 2. and then on the left hand side of the equation I cover up the x minus 2 bracket and I put the value of x equals to 2 wherever I see an x in the other term. So to find a in this case, in the numerator I'll get 2 times 2 plus 3 over 2 squared plus 3, that gives me 7 upon 7, so a is equal to 1. Example 3 continued. I've just repeated equation 3 for convenience here. I'm going to use the comparing coefficients method. Now, in this particular example, we actually have x squared terms, x terms, and constants, so I can generate 3 equations if I wanted to, one for the x squared, one for the x, and one for the constants. But because in this particular question I've already found the value of a from another method, I only need to generate 2 equations. So I'm going to compare coefficients of the x squared terms to get my first equation. On the left hand side of equation 3 I have no x squared terms, so that's 0. On the right hand side of equation 3 I have an ax squared term and a bx squared term, so my coefficients there are a and b. I already know the value of the a, it's equal to 1, so putting that into the equation and rearranging, I find that b is equal to minus 1. If I now compare the constant terms to generate a second equation, on the left hand side of equation 3 I have 3, and on the right hand side my constants will be 3 times a, if I expand the bracket there, and also the minus 2c in this case. So 3a minus 2c are the constants on the right hand side. Again, we know the value of a is equal to 1, so I can put that into the equation. And if I rearrange this equation, I actually find in this particular case, it's not always the case, but in this particular case, constant c is equal to 0. I now just need to write the constants into the original partial fractions, so a over the x minus 2 plus the b in this case, which is minus 1x, plus the c, which is 0, over the x squared minus 3. The last line I've just tidied the equation up. Okay, leave you with some tutorial exercises on quadratic factors here. In exercise 1, if you notice in the denominator you have a quadratic factor, the x squared plus 2, and a linear factor, the x plus 1. So your solution sequence of partial fractions will be ax plus b over the x squared plus 2, and it will be plus c over the x plus 1. And your a, b and c constants are given in the answers. For exercise 2 here, in the bottom line you have an x squared times an x squared plus 3 in brackets. This is a repeated linear, the x squared, and the x squared plus 3 in brackets is a quadratic. So in this case you will have a over x plus b over x squared plus cx plus d over the x squared plus 3. So this would be your a, your b, your c, and your d terms here. I'll let you look at example or exercise 3q and attempt that on your own. Some further tutorial questions to look at here on linear and repeated linear fractions. Thank you for viewing.